Hello, my name is Abarca and I am a PhD student at IUSS Pavia. In this video, I'm going to be presenting a little bit about the work that we did for regional assessment of bridge infrastructure, which was carried out within the context of the InfraNet project. InfraNet was an European funded project. It was partially funded by the DG ECHO scheme. It was a 24-month project. It dealt with the regional seismic assessment of bridge infrastructure within 3 countries: Italy, North Macedonia, and Israel. The project was carried out by 3 partners: EU Center, which was a representative of Italy and was also the project coordinator; IUSS, which is a research institute in North Macedonia; and Yaronofir Engineers, which are a private firm in Israel. In terms of the methodology, InfraNet was basically a risk project, so what we took was a very vanilla approach of a risk framework, basically dividing the work into each one of the main components of risk, namely hazard, exposure, and vulnerability. In terms of hazard, we were dealing mostly with seismic risk, so the question that we needed to answer was: how big are the earthquakes that are in each one of the regions? What can we expect for the intensities in each one of the locations? How frequent and what are the magnitude of earthquakes that I can expect in each one of the locations? Once that we have this, we needed to know where are the bridges located, what are my exposed assets, and furthermore, what are their characteristics, what are their mechanical properties, what are the material properties, what is the structural layout, as much as information as we can gather from all of the bridges. Finally, in terms of vulnerability, the information from the hazard and exposure is combined and analyzed so that we can derive fragility curves for both damage and collapse of each one of the assets in our database. What these fragility curves do is that they correlate an intensity measure level coming from the hazard component with a probability of exceeding a specific limit state. Finally, everything is integrated into the web-based platform. In terms of the hazard component, the first thing that we did was to take the most updated available seismic models for each one of the countries. Once this is done, the hazard component is divided into a 3-step process. The first one is the site-specific hazard. Up here, we combine the soil characteristics that we take from the VS30, taken from the global datasets of USGS. And down here we have the seismic potential, let's say, as in this case, PGA for 475 years. This is combined with the location of each one of the bridges, and what we do is that we do an overlay of all of this information. Within here, we identified interesting combinations between soil characteristics, seismic hazard, and location of clusters of bridges so that we can define specific hazard sites that are of interest for our research. Typical results, which would include hazard curves and uniform hazard spectra for each one of the sites. The second step, or the second component within this 3-part process, is disaggregation. So we do this for every site, and we do this for 7 return periods, which range between 100 years and 10,000 years. This information would tell us what is the magnitude and distance that mostly contribute to a specific intensity measure. We take all of this information and we perform record selection. This is going to be needed further down the line within the vulnerability component for us to run nonlinear time histories and calculate fragilities for each one of the bridges. In terms of exposure, we need to know how much information we can collect for bridges in each one of the countries. An exposure model, which is the overall goal of this component, is basically a georeference database. For each one of the bridges that I can locate within a specific case study, I'm going to create a database. And this database, ideally, would contain information of all of the bridges in terms of location, what is their structural system, what is their taxonomy, what is the dimensions, detailing, inspection reports, material properties, any information that we can get our hands on. Real case problems typically range within the thousands of bridges, which are already been constructed for decades, meaning that it is very difficult to obtain complete information on all of the assets within a network. For InfraNet, what we did was that we took information from multiple sources and we classified them based on the information level. So we have level 0, for example, which is basically just the location and length. This is information that we take from OpenStreetMap layers. We have information level 1, which is a little bit more information. Basically, we have the structural system. We have some idea of the materials in terms of if it's a steel bridge or if it's a reinforced concrete bridge. And we have generally incomplete geometry. This still would be insufficient to create a model, but it would be enough information for you to classify it within a taxonomy branch. Then we have level 2 information, which is a lot more complete. This is typically gathered from inspection report. Level 3 information, which is basically the one that you obtain from blueprints. Here we can see an example of the level of breakdown of information that we can procure for this type of analysis. So we have detected 4,400 bridges within OpenStreetMaps. We have over 500 bridges for level 1. We have 47 for level 2, which we did inspections for. And we managed to procure 17 blueprints from bridges within this area. This is a typical breakdown and very similar to what we found for North Macedonia and for Israel. All of this information is stored in a database and it constitutes our exposure model. Now, about the vulnerability component, we need to know how fragile are our bridges. Since our information from exposure is basically incomplete, there is no way for us to actually calculate the specific fragility of each one of the assets. For this reason, we took a taxonomy-based approach. Now, this is the overall methodology of a taxonomy-based approach. So basically, we would have our bridge database from the exposure component, and then we would break down all of the information from that database into different characteristics. Now, we may not be able to exactly calculate the fragility of each one of the bridges in our database because we don't have enough information. However, what we can do is that we can calculate a mean fragility for a family, and if a bridge is able to be classified into that family, it is assumed that it's going to have a behavior which is going to be close to that mean. Once that we have defined this, we run everything through a calculation engine. This calculation engine is basically a set of codes which take information from our database and creates numerical models of each one of the assets that we have and run nonlinear time histories. Based on the results of this nonlinear time histories, it's going to produce sets of fragility curves. These sets of fragility curves are then processed, and the mean fragility curves per taxonomy family is then assigned to each one of the bridges in our case study, which has been identified to each one of those taxonomy branches. Since in our database we don't have enough samples of bridges within each one of the taxonomy branches, we needed to create some synthetic models so that we could completely characterize a taxonomy branch. So for example, we take a look at this bridge. We only had, let's say, 20 samples of this bridge with complete information so that we can run analysis. But what we could do is that we could do a statistical analysis of the structural properties of all of the bridges within my inventory that had similar characteristics, and we can use this information to sample representative bridges. These bridges don't actually exist, but they're considered to be representative of each of their taxonomy branches. Once that we have enough numerical models to represent each one of the taxonomy branches, we go into the fragility calculation stage. In this stage, for each one of the models, we're going to run nonlinear time histories with the selected records from the hazard component. The intensity measure that was chosen was average SA within the period range of 0.2 to 1 seconds. Just to give you an idea of the volume of work that this took, we have 30 earthquakes per return period. We have 7 return periods ranging from 100 to 10,000 years. We typically have 50 bridges per taxonomy. Now, if you consider that overall for the 3 countries we defined 21 taxonomies, this means that we carried out over 220,000 nonlinear time history analysis. Once that we have all of the results, we group them into each one of their taxonomy branches. Here, for example, each one of the gray lines would represent the fragility curve of each one of the numerical models that we did, and the green one would be the mean fragility for that specific taxonomy branch. This fragility values can be combined with the results that we get from the hazard component and with the replacement cost for each one of the assets so that you can have direct loss results. Now, in this project, we were also interested in the indirect losses. Bridges form part of complicated road networks. Once a bridge is severely damaged or it collapses, it's not just a matter of replacing that bridge, but the time for which the bridge is not there, that's a disruption on the road network, and that's also a cost, indirect cost, which has to be assumed by the users of the road network. Now, for you to actually calculate a monetary value for indirect losses, this is a very complicated exercise, which has to do with road network modeling, as well as having information for how the people move within a specific traffic system. Now, this information was available for Italy, but it wasn't available for North Macedonia or Israel. We were able to implement an algorithm, a very simple routing algorithm that calculates an optimal route between two given points. Since we have control of the network, we can also define a barrier or a disruption. In our case, for example, a bridge collapsing. Once that you have this disruption, we can just remove that link from the network and the platform will recalculate the next best option for routing. The way that we use this capability so that we could calculate or have an idea of indirect losses is that, for example, within our network, we could run that algorithm to and from each one of the points. So this would be a single user traveling on the uncongested network, going from A to B, from B to C, and from C to A, back and forth. With these values, we can have a baseline travel time matrix. Afterwards, we can, for example, simulate a seismic event, and if we determine that two bridges have collapsed, then we can rerun the algorithm going to and from each one of the locations, and we can have an interrupted travel time. Once that I have this information, I simply can divide both matrices, the individual values of each one of the matrices, and this way we define interruption coefficients. Now this coefficient, sadly, they don't give you a value of the indirect loss, at least in monetary value. But what we can do is that we can, for example, average the non-diagonal values, and this will give you an idea of which communities were more impacted by an earthquake. Furthermore, I can also do an event interruption index, which is basically just the average of all of these coefficients. And this would be for me to compare, for example, between two seismic events, which one was more damaging to the overall network. Now, finally, just to talk a little bit about the web-based platform, it's available at this link. All of the information that was collected is there. People cannot edit or download that information, but you can view and you can run calculations based on, scenarios for specific earthquakes that you want to see what might happen, what are the probabilities of collapse for each one of the bridges, and, for example, run some specific routing exercises like the one that I was showing before. Now, finally, I just wanted to give a couple of remarks. This is not actually conclusions, but I just wanted to say that there is a lot of information that was carried out within InfraNet that I wasn't able to talk about within this presentation. But feel free to go to the project website. Also, there's a lot of research that stems from this project, so feel free to check out the YouTube channel of our research group, which is Rose Center. And that's it for me. I hope that this was very useful and have a nice day.